everyone. Thank you for joining today. We want to start off by providing a quick introduction to Delta Analytics and our Teaching Fellows program. Delta Analytic is a 100% volunteer-run nonprofit organization based in the San Francisco Bay Area. Our mission is to increase the usefulness of data to empower change makers working to better their communities. We work towards our mission through our two core programs. Our Data Service Grant, otherwise known as our Data Fellows program, works to bridge the nonprofit skills gap by pairing our Data Fellows with nonprofit. Our Machine Learning for Good program, otherwise known as our Teaching Fellows program, aims to empower everyone anywhere to leverage data for good by building technical capacity through the world. As an organization, since 2013, we have completed 15 projects with nonprofit and social impact organizations on the Data Fellows side, and open sourced and taught our machine learning curriculum to students globally on the Teaching Fellows side. This was done with the volunteer efforts of over 200 data professionals. With their efforts, we have been able to donate over 20,000 hours and charge $0 for our services. Wanted to give a brief introduction of our Teaching Fellows program specifically. So Delta has been working since 2013 to help nonprofits around the world with their data. In 2017, we started the Teaching Fellows program. Some of the things that we have worked on over the past few years is build our curriculum from scratch, taught our pilot programs in Nairobi, Kenya, beta tested, revised, and open sourced our curriculum. We also taught subsequent classes in Morocco and the Bay Area. We also explore supplementing our curriculum with active learning techniques. And finally, this year, we have expanded our program to support educators all over the world. So now meet our 2020 Bay Area Teaching Fellows. These are the people who support the whole programs and run the operational side of the programs. And also, we are very thrilled to introduce our 2020 Global Teaching Fellows through this series of virtual machine learning talks. So in today's lecture, our Global Teaching Fellows is Krish, and Krish will give us his talk on Bayesian Machine Learning.
All right. Hi, everybody. My name's Krish, and today I'll be talking about Bayesian machine learning for my graduation lecture. So a little bit about myself. I'm currently an undergrad at Northeastern University, so I'm entering my second year where I'm studying computer science and mathematics. So I have about 3 years of experience in machine learning research. So originally, my interest was in biomedical imaging, so understanding where we can predict diabetes based on MRI scans, as well as breast cancer prediction to have better diagnosis for those patients. More recently, my interest is in propagating uncertainty, so hence the Bayesian machine learning talk, as well as in using generative modeling to understand where we can propagate uncertainty in the output space to have more interpretable deep learning models. So the things we'll be going over today are, what does it mean to be Bayesian? How can we use a Bayesian approach in machine learning? And then we'll go over a quick coding example of leveraging Bayesian techniques for machine learning. So what does it mean to be Bayesian? So the real importance of Bayes' rule is that in real life, there are cases where a probability may be difficult to directly observe. So for example, very pertinent today, the probability somebody actually has COVID if their test came back negative or positive. Now, we can't observe directly whether they have COVID. We can only test whether they do. But we might have information about the related quantities to these tests. We may know the false negative rate of these tests and the probability of getting COVID in general. And so what we can do is we can leverage a technique of conditional probabilities to infer information we don't currently have. So what does it mean to be conditional? Conditional probabilities are just probabilities, but you know a certain related quantity to already be true. So more generally, what is the probability of B if I assume A to be true? And then we account for the probability of A in the first place. So in traditional coding structure, if you have an if statement and then you have a condition, once you enter that if statement, you know that condition must have had to be true in order to get to that location. But then you can account for the probability that the if statement condition was true in the first place. So let's get into a little bit of the mathematics of this. So the structure of Bayes' rule is if we have a event A given B, we can write the probability of event A given B as the probability of event B given A, which is this bracket right here. So the bracket means given, and then we would multiply that probability by the probability of A and divide by the probability of B. So again, this is the probability of event A given that event B has already occurred. And we can use this formula because we have information about A and B separately, notably the probability of A and the probability of B. And we have some information about B given A, which is seen in the numerator. So what's interesting is that if we have some information that we know these two events, A and B, aren't really interacting at all, meaning that they're independent, this formula simplifies really nicely. So when probability of B given A is not related, so the probability of B is not related to A, that would just be the probability of B alone. And then what we see is we have this term of probability of B in both the numerator and the denominator. So using our mathematics skills, we can figure out that the probability of A given B is just the probability of A, since those two would cancel out. So more generally, what this means is if A and B are independent events, the formula simply reduces to the probability of A given B being equal to the probability of A. So now let's look at a certain example. I love playing soccer, but I really hate practicing in the rain. So I know today it's raining, and I want to determine how risky it is for me to skip practice. So essentially what I want to know is, can I use the data that I already have from last season to determine the probability that we have practice today, given that it's raining outside? So I gathered some statistics from last year. I know that we practice on 80% of the days during the season. And of the days that we practice, 10 of them are rainy days. 10% of them are rainy days. And I know in general, it rains 20% of the days during the season. So now we can formulate our target probability as a probability that we're practicing, given that it's currently rainy. So now we will use what we have covered previously, which is essentially Bayes' rule. So let's look at those statistics again and try to map them to a certain probability. So we know that the soccer team practices 80% of the days of the season. So we know in general the probability that we're practicing is 80%. Of the days that the team practices, only 10% are rainy days. And so in formula, this is probability of rainy given practicing is 0.1. Finally, on average, we know that it rains about 20% of the days. So we know the probability that it's rainy is 0.2. So given that it's rainy, what's the probability of practicing? Our target, again, is the probability that we're practicing given that it's rainy. So using our formula from last time, which is a probability of A given B is equal to the probability of B given A times the probability of A all over the probability of B, we can use some substitutions to structure this for our own problem. So what this turns out to be on the bottom left here is that the probability that we're practicing given that it's rainy is equal to the probability of rainy given that it's practicing times the probability that we're practicing all over the probability of rainy. So now we have the individual components for each of these things. So we see that the probability that we're practicing is 0.8. So we can sub that in right here. So just plug that value in on the right. And we know the probability that it's rainy given that we're practicing is 0.1. So we substitute that in right here. And then the last piece that we need to substitute is the probability that it's rainy, which is 0.2 as we've seen. So we just take this value, plug it in here. And at this point, this is just a calculator operation, which tells us that there's a 40% chance that we're practicing today. So it might not be the best idea for me to skip practice today, even though I hate practicing in the rain, because there is still a good chance that we're still practicing. So now we're going to look at something known as formulating the posterior. So we'll use the information that we know about Bayes' rule and try to determine a related but not identical relationship. So you'll see that this sign right here is no longer an equal sign, but rather what this symbol means is that the quantity on the left is proportional to the quantity on the right. So we already know some information, right? So we know the probability that it's rainy, which is this prior distribution. This is our information that we already knew prior to our current situation. And so we know that was 0.2. Great. So now we want to know, based on some data that we've collected, what is the probability of rainy given practicing. So what we can do is we can say the probability of practicing given rainy is this likelihood. And this is some evidence that we have that we can use to calculate this probability right here. So once we have that, we can determine the thing on the left, which is this posterior distribution. So once again, this is going to be our prior information. This is the data, which we refer to as likelihood, which comes from the statistics we collected from the previous season. And that gives us ultimately this posterior distribution, which is what we can infer by combining what we already knew, and which is our prior, and some information that we collect as data. So ultimately, this gives us a generalizable formula, which is this posterior distribution. The probability of A given B is proportional to the probability of B given A times the prior, which is the probability of A. So each of these terms in this proportional relationship have a name for them. So just like this previous information that we generally know is a prior distribution, likelihood is the data, and finally the posterior distribution is something that we can't observe, but we can formulate a distribution for based on the data that we have collected and our information from before. So what this gives us ultimately is a distribution relationship rather than a relationship that is just singular values. So since probabilities come from distributions, we can generalize Bayes' formula to be a proportional relationship between distributions rather than just values. So let's think about this in a concrete scenario. We want to find a distribution of player heights in the league that we play in for soccer. And we know we pick our players using a certain criteria. We want the majority of our players to be tall because central attackers, defenders, and goalies all have to be tall to either head the ball away or head it into the goal or protect the net. But we're okay with some positions being shorter players. So, outside attackers or outside defenders, it's all right if they're shorter because they're not really in critical positions where if the ball is in the air, they need to really win it. So we also know some information about heights of people in general. And this is our prior information. So it's not specific to our task, but it's certainly information that we know about a population. So we know that heights in general are normally distributed. So this is known as prior information. And we know that the heights follow something known as a normal distribution. So normal distributions show up a lot of times in nature. And the reason for that is, that we follow a bell curve for many pieces of data. And so what happens is the way you parameterize a normal distribution is by where the center is and what the standard deviation is. So we know that our average height is 70 inches. So sorry for those of you that aren't from the US, but inches are kind of the standard unit of measurement here. So we know that the mean is 70 inches, which is just another word for the average. And we know that the standard deviation is 3 inches. So that means this distribution right here is centered at 70 inches, and one standard deviation to the left is less than 3 inches less than our average, so 67 inches, and accordingly on the right. So this essentially notates the formulation for each location on this distribution. So we know the majority of heights are clustered around here, right? So in this range from 67 inches to 73 inches. But we know some data here, which is how we pick our players. So we pick players because we want the majority of players to be tall, but we're okay with some positions having shorter players. So let's use this information to come up with a distribution for the player heights in the league. So this is, of course, going to be an approximate distribution because it would be a little absurd for us to collect the data on every single player in the league when we don't have the resources to do that. So now let's keep this in mind when we're thinking about how we pick our players. And we find that based on our data from tryouts, this team that we picked, we can find an approximate distribution using that proportional relationship we've talked about for formulating a posterior distribution. So we can say that the approximate distribution for the heights of players over the entire league looks something like this. And this matches kind of our intuition, right? Which is that there should be a small peak where there's shorter players, but the majority of players should be clustered in this area. And so what's interesting about this proportional relationship that we found is that no longer are we only restricted to a simple representation of our data. So originally we had a normal distribution, which gives us some information, but it doesn't give us more information about our specific scenario, which is talking about soccer players, compared to the general population, because our prior information is only restricted to the context of every person in the entire world. That's the distribution we've collected from there. Of course, that's somewhat approximated based on the law of large numbers, but that is a bit beyond the scope of our discussion. So what we're able to do is we're able to use this formula right here, this proportional relationship, that the probability of heights of players in the league, given our tryouts, the team we selected from our tryouts, is equal to the distribution of tryouts given their original heights times the distribution that we found of the heights originally. So this formula is a bit of a generalization when it comes to implementation of trying to find a posterior distribution based on similar data like this. There are nuances, but the general concept is that if you have some prior information, a prior simple distribution, and then you collect some data about a specific situation, which is still related to the prior distribution. So in our case, the heights of players that we picked for our team, which is the data we collected, compared to the general information we know about the population's heights. We can formulate some inference about the general distribution of heights of soccer players in the entire league, only based on our team's data and the data we have about heights in general. So now let's generalize this to beyond just the case that we talked about with soccer player heights. So understanding a prior and posterior distribution. Our assumptions or prior knowledge about the data allow us to make a choice for a prior distribution. So in our case, we know that heights are normally distributed, so we picked a normal distribution and then parameterized it using the two parameters that we do use to define a normal distribution, which are revisiting this mu, which is where the distribution is centered, or the average, and the standard deviation. So we picked two specific parameters for that. We picked 70 inches as the average, and then 3 as a standard deviation of heights within that distribution. However, using evidence, which is data, we learn an approximate distribution of the general situation that we want to model. So this is an inference, right? So we can go from something that's really simple and not very informative. So informative in the sense that it doesn't really model the true distribution of our data, to something that may not exactly resemble it, but it's certainly a better approximation, right? Because we know that as a coach, we want to pick a small number of players that might not be as tall, but might be very skilled, but we want the majority of our players to be tall. And so while the normal distribution doesn't really represent this, even though it's a distribution of the general population's heights, we can learn this posterior distribution, which approximately does show us that, where we have a large number of players that are falling under this region right here, but there's a smaller number of players that are falling under this region right here. So if the x-axis is the heights and the y-axis is the concentration of the players or the number of players, we see that there's a lot more players in this cluster right here of tall players compared to this cluster right here of short players. So a quick check for understanding. So what I'll do here is I will read the question out loud, give the options, and then wait a couple of seconds to allow the audience to kind of come up with their own solution, and then we'll go over the answer together. So this is about Bayes' rule, and it's kind of related to the situation we discussed earlier. So how would we predict the probability it rains given that it's cloudy today? What would the formula be? So what we're looking for is a probability of rain given cloudy. All right, so we can say that the probability of rain given cloudy is the probability of the opposite, so probability of cloudy given rain times the probability of rain over cloudy. So that would be option C. So let's go through the other options as well. So we know option B isn't really realistic, right? Because this is just a probability of rain, whereas we want to know the probability of rain given some information. So this follows the same form, but the equation isn't quite correct. So here we have the probability of cloudy times the probability of rain over the probability of cloudy and rain. So in this case, the terms are correct, but they're not arranged properly. So again, going over the correct answer, we know the probability of A given B is the probability of B given A. So this follows that little flipped relationship. And then once you flip, you multiply by the second piece of this, which is the given part. So you multiply by probability of rain all over the probability of cloudy. Great. So now we're going to move on to a naive Bayes example. So this is a ML technique where we want to solve a concrete problem. So the way this formulation works is that we determine the probability of class given data. So that's some sort of evidence that we have for every single data point. So we multiply the probability of data point 1 given a specific class times the probability of point 2 given a certain class. And we know the probabilities that each of these points belong to those classes. So that's data we've collected. But that's a little abstract. So let's go into an example where we've collected some data. So this goes back to that scenario we were talking about. Now, no longer do we only have those statistics, those summary statistics that I discussed, where we have practice 80% of the days, it rains 20% of days, and we practice when given that it's rainy on 10% of days, right? So that's not exactly the same format of data we're looking at here. This is more of the raw numbers that we've collected. So let's look at these likelihood table, right? So these right here are the likelihoods, and we can manually perform the calculations we've done previously. So let's consider the probability of sunny given that we practiced. So the way we want to do this is we want to determine the probability that we practiced given that it was sunny. So the way we do that is we look at the row that corresponds to the weather that we're considering, right? So the probability of this is something we already know. It was already sunny, so we don't have to consider the other values. So when we're looking at sunny, we want to know how many times do we practice out of all of the times that we could have practiced. So the way this works is that we sum up the times that we practiced over the number of times we practiced plus the number of times that we did not practice. So this essentially is this right here, this practice term, because it's in the sunny row, and it's over 15 plus 1. So that's the denominator here. And we multiply that by the probability of sunny. So we want to know out of all of the days and all of the weathers, how many of the days was it sunny? So we're considering 30 days, and 16 of those days it was sunny. So that's why this right here, the probability of sunny is 16 over 30. So that's the likelihood. And then we divide by the probability of practiced, right? So this is just the sum of all of the days that we practiced over the total number of days. So here it's 20 over 30, so we divide by 20 over 30. Now let's look at the case where we want to know the reverse. We want to know the probability that we practiced given that it's sunny. So the way we consider this is that now we want to look at this first probability as a probability of sunny given practiced. So we could directly plug this in, but let's think about how we can use this table to find that value. So now we know that we practiced, right? So the first term would be sunny given practiced. So we know that we already practiced. So we can restrict our search for the value into this column right here. And now we want to know of the days that we practiced, how many of them were sunny? So we know 15 of them were sunny, and the number of days we practiced was 15 plus 3 plus 2. So that's 20 days. So that's why this is 15 over 20. And now we want to know the probability that we practiced. So that, like we saw previously, is just going to be 20 over 30. So that's the total number of days we practiced over the total number of days that we're looking at, which is 30 days total. And the way we find that denominator that I've been referring to is we sum up all the values on the inside of this table. So we sum up 15, 1, 3, 4, 2, 5, which all totals to 30. So that's why that denominator has been so common, and that's why it's the one that's on all of the outsides of the tables under the likelihoods. Then we divide by the probability that that it was sunny. So the way that we've done this previously has just been the exact same. So the probability that it's sunny is the number of days that it was sunny over the total number of days that we're looking at. So that was 16 days it was sunny. So we divide by 16 over 30. Great. So now let's talk about something that's very different. Let's discuss neural networks. So the first question is, what is a neural network? So a neural network is composed of individual units, which are known as neurons. So let's look at this diagram right here. So we have the inputs to our neuron, which let's call this our neuron, the hidden layer, and then we have this output. So we have inputs, some computation, and an output. Those are our 3 steps. And now this does look a bit complicated. So we have input x1, we have input x2, and we have input x3. And each of those are drawn together or passed into this hidden layer where this computation is happening. And so you'll see when they're passed in, there's this corresponding weight. So, in a graph, you have nodes and edges. So this is a node, this is an edge connecting this here. So what we would do is we take the input, we multiply it by this connecting weight, and then we pass it in here. Then we do the same for every single input. We have this input, we multiply it by this weight, and we pass it in. We take this input, we multiply it by a weight, and we pass it in. And then you'll see this right here. So this is a summation. So we're going to sum over all of the inputs, and so we have 3 inputs where m would be equal to 3, and we sum up the weight times the input. So while this sounds complicated, it's very similar. In fact, it's exactly a neural network or a neuron that is performing this linear regression type approximation, right? So we would obviously have to optimize. We would have to pick weights, these W terms, that minimize our difference between the prediction and the true value of Y. But the computation is identical to linear regression. You have an input and you have a corresponding coefficient. You have an input and a corresponding coefficient. You have an input and a corresponding coefficient. And that's all that's happening here. So in neural networks that are used in cutting edge applications and in general, they have this thing called an activation function. So that's something that is a non-linearity that's applied, which is a bit beyond the scope of our discussion. But for the sake of the concept, the way this works is that you just have inputs, they have corresponding weights, think of them as coefficients, and you sum them all up and apply some operation, which gives you this output. So in our case, the operation we're applying is just a summation, and we right now have these point estimates, right? So each of these is going to be a singular value. This could be 1, 2, 3, 4, 5, and the same thing for these values. So you only learn a single value for each of the coefficients. But now we've been talking a lot about these distributions, probabilities, and so we know that probabilities and the probability of an event comes from a probability distribution. So what if, rather than pulling these values as just individual scalars or single values, what if we learned a distribution of possible values that each coefficient could take on? So let's think about this visually. This is essentially applying a Bayesian outlook to neural networks. We no longer want to learn a point estimate over each coefficient or weight. We want to learn a distribution. So let's walk through this diagram. We have this input right here, and it is being passed into each of these neurons. So like we said before, a neural network is just a stack of neurons. So this is the exact same diagram as we saw on the last page, except we have multiple of them. So now when we have these connections, these have corresponding values, right? So x1 here would be multiplied by 0.1 and passed in here. Here it would be multiplied by 1.2 and passed in here. Here it would be multiplied by 0.3 and passed in here. And so that's useful, and it will give us a prediction, but every time I have the same input value for x, we're going to get the same output value. And that might not always be true in nature. So what we want to see is what are the possible outputs that this neural network might be predicting. So the way we do that is we learn a distribution of values. So now, while 1.2 might exist in this distribution for this connection right here, it's not the only value we can get. We can sample from this distribution for the possible weights that might be in order to pass in different, multiply the x value by a different value here every time we're passing it forward. So what that overall allows for is multiple times when we run this network, we're going to get different outputs. And oftentimes in computer science, that's not something you want. Every time you run a program, you want the exact same output, or else there's something fishy going on. But when we're thinking about probabilities, we want to think of what is the entire possible range of values this can take on, which ones are most likely, and let's think of that as a distribution of values that we can learn. So overall, we learn a distribution of possible networks, right? So every time you sample, you're essentially sampling from a different network. So every time you pass in an input, a different value will be selected at each of these connections. But they're still extremely likely values for that connection to take on, which gives you a distribution of possible outputs and a distribution of networks that are predicting those outputs. And so overall, what that means is we're able to capture uncertainty about specific parameters. And what we can do in the output space is then we can understand the variability that we have in our predictions, and that can allow for us to capture uncertainty. And this seems like a really abstract concept, and it certainly is. So what we'll do is we're now going to look at a coding example just to discuss some of the pieces that we can see visually in terms of the importance of capturing uncertainty. So just to review this slide, because I know there was a lot of content here, we're no longer learning point estimates. We're no longer learning individual values. We're learning distributions. Just like when we saw we want to approximate a posterior distribution, that's what we're doing here. We're learning a posterior distribution over each of the weights so we can extract information about the distribution of values it might take on rather than a singular value. Originally, we assume each weight follows a approximately normal distribution. And so the reason for that is oftentimes in nature, things do follow a normal distribution. And in fact, here, if you had many more connections, you would see that the values do generally follow a normal distribution. And so what we ultimately end up doing is we learn a distribution for every parameter, and we know the wider a distribution for a given parameter, the more uncertain we are about it. And so, let's look at a concrete example here. Here, the distribution is very narrow. Here, it's very wide. So we're more uncertain about this parameter than we are about this parameter. So let's take a look at what this might look like in application. So first, before we go to the coding example, I want to share another check for understanding, which is related to the topic we just covered. So in Bayesian neural networks, are we learning a posterior distribution over the output or the weight space? All right, so going over this question, so first of all, the answer is that we're learning over a weight space. And the reason for that is because we're placing a distribution over each of the weights. We're learning a distribution for the weights, not for the output. And while we might be able to get a variation of outputs, the way we're learning, the posterior distribution we're learning is over each of the individual weights. So that's referred to as the weight space. So the next piece is a coding demo. So we'll be going over Bayesian linear regression. So let me just change tabs here. And I'll zoom in a bit more. All right. So let's think of a concrete scenario. This season, I have the option to coach a team. So the organization has very kindly given me the opportunity to choose which team I want to coach. And I'm someone who likes to observe a lot of goals during the season. So I want an entertaining season, which for me involves a lot of goals. And the way I want to do this is by using data that I've collected from the past season. So I know the average player age on every team, and I know the average goals per team in that kind of age group. So here we see there's a weak positive association here, right? So that means I can draw a line approximately here, and I know it will be a little, it will have a positive slope. So we know that there's generally a positive linear association here. So that's just basic linear regression. But there seems to be a lot of variability around here. So what I want to do is I want to gain an understanding about how uncertain is my linear regression. Essentially, what is the variability in my prediction for, let's say, if I want my linear model to predict how many goals I should expect if the average player age on my team is 15, then I want to know what is the distribution in terms of how uncertain my linear regression model will be. So the way we do this is we use Bayesian linear regression. So there's some boilerplate here, but I want to focus on a specific part of this. So we're going to fit a Bayesian linear regression model. So let's look at this function right here. So we have this input x, so x is a matrix, and y are the prediction values. So x are the input features. So in our case, we have two input features, which we're going to look at, and we have a target output. So one of those features is the player age, and the other feature is, let's go take a look at our visualization. So the other feature that we're looking at is the games that they won last season. So now that we have those two data points, we want to look at this right here, which is this fit Bayesian. So we have a matrix input where we have our average age, and we have wins last season. And our target output is the number of goals. Great. So now we are going to model a relationship that follows the traditional structure, which is y equals mx plus b. And so this is nothing all that unique, right? We're still learning a coefficient for each of our inputs. So in our case, we'll have two mx terms. So we'll have m1 x1, and we'll have m2 x2, one for each of the features that we're passing in. So now the way this works is a bit complicated, so I'm going to go over the math, but it's certainly the proof of this and the reason it works is far beyond what I can cover in this lecture. So I do want to share it because it's important, but don't focus all too much on it. The importance is the concept and what value does this provide, because the implementation is something that can always be focused on, when the time comes to code this up. So the way we draw this is that we have this beta function. This beta is what we're looking to learn. This is the model that we want to learn. And the parameters for that come from this normal distribution. So we have a mu, which is our average, like I said earlier, and then we have our variance. And the reason we have this I is that's the identity matrix, which gives us a covariance matrix. But for all purposes, what this looks like visually is essentially this diagram right here. This is a multivariate Gaussian distribution or a normal distribution, and it essentially occurs when you have more than one dimension, right? So your normal distribution is over multiple variables, so you have a distribution that spans multiple dimensions. So all we've done is we've gone from 2 dimensions where we have a bell curve to essentially a 3D bell. The shape is still the same, and the concept is just generalizing to a higher number of dimensions. So that's all I really want you to think about here, which is this is just a 3D bell curve, or just a bell in fact, because it's no longer a curve. So we're sampling from this bell, right? So that's all that's really happening here, and we're specifying where that bell is centered and what the variability looks like along each of the axes that we have, or each of the dimensions. And then what we have is that we have our y, which is given as this function, which is x, the input features, times the coefficients, right? So this is just regular linear regression where we have this beta, which is the m, this right here, right? So beta 1, beta 0, and those are just being multiplied by x1 and x2 respectively. And then we have variance for that distribution as well. So once again, you're going to have this variability across each of those parameters. And what's interesting is just as with regular linear regression, there's a closed form solution. So the way this works is that you incorporate the variability directly into the closed form solution. So once again, I don't want to get into the technicalities, but I will certainly show how this is computed at each step. And the proof for this and the reason why it works is, again, beyond the scope of our discussion today, but it's certainly interesting, and I definitely encourage you to look at it. So these are just matrix operations that we're performing. And a closed form solution will instantly provide us with the coefficients that we're looking for. And this is in comparison to something known as gradient descent. So if you've discussed parameter optimization, you'll often talk about this operation known as gradient descent, which is great when you have a lot of parameters to learn. And in our case, we're using a closed form solution just because that the gradient descent process would take a little bit longer, and it's not something that I want to really focus on. So here we have the computation that we're performing. So this is the closed form solution right here. So this right here is a closed form solution, and we're going to break it down over here. So we have this variable that we're assigning, L, which is equal to sigma squared times the variance times I. So as you see, this is highlighted right here. So this is what we're computing. And then we add that to x times x transpose. So this is the input times itself plus this term. So we've simplified this. And then we invert that matrix. So this is an invertible matrix, so we find the inverse. And then we multiply it by x again and y again. So matrix multiplication works a little bit differently, which is why we're doing a dot product here. And then we save the variance of the posterior distribution that we've learned, right? So like I mentioned here, that's essentially what we're saving for right here. This the prediction, what we're looking to predict given our input and our coefficients, that comes from a normal distribution with this variance. So all we're doing is we're saving the variance because we've saved our function as beta. So what this looks like visually, and that's really what's most important at this point, is that we want to look at what does it look like once we've trained this Bayesian linear regression model. So we start with only 5 inputs, right? So we have 5 data points, and our variability is very extreme because you see these light yellow lines are the possible linear regressions that are drawn from the posterior distribution of the possible target linear regression line. And this orange one is essentially the average of all of those, right? So the average of all of these samples that we've drawn, so we've drawn samples from our posterior distribution, and the average of all of those is this bold orange line. But each of these are individual samples that we drew from the possible distribution of lines. And so we see that this provides us significantly more information than just directly trying to optimize our parameters. And we see that we're quite uncertain in the number of goals that we should expect from these players. And as we continually add more and more data points, the light yellow lines, which are each of the samples, the interval of them, or how widely they're distributed, that begins to narrow down. So like we discussed previously, when we look at a posterior distribution, the more narrow it gets, the more certain we are about our samples, right? About the distribution or about the true value that it may take on. And when we add 50 and 100, we see that's super tight. So that this concentration of samples is in a very limited range. And we see that this fits almost exactly our standard linear regression, but we should expect some variability. Standard linear regression wouldn't give us that information, but Bayesian linear regression does. So particularly when we have large variability or some critical application, we can know that we should expect some variability in our prediction. And so, if I was to sample from this line, I know that there's a certain range of possible lines that I could find in that range that I should expect. So I should expect some uncertainty. Great. So now let's look at another interesting visualization, which is for our parameter posterior distributions. So like I mentioned earlier, this is from a multivariate distribution, right? So we're looking in multiple dimensions, which is why we're not only looking at what is the 2D curve that an individual parameter follows. So what we've essentially done is we've taken that 3D bell and we've squashed it onto a 2D plane. And the colors essentially indicate how dense the concentration is at that point. So I want to emphasize this a little bit more. So let me scroll back up to our multivariate distribution right here. So where there's a lot of points, which is in this red region, if we squash this, we are essentially mapping the colors into a 2D plane for how concentrated the values are at that region. So now if we look at these plots right here, we can say that there's a lot of samples that come from this region, a little less in this region, very few from here, and none in this area over here. Great. So now that we've explained this visualization, let's look at the axes and try to interpret what's happening. So we know that average team age and our games won last season are our two input features, and the axes are essentially the coefficients that we've learned. So this is the distribution of the coefficients. So this is for 5 samples, this is for 10, 50, and 100 correspondingly. And so what we see is that the posterior distribution gets tighter and tighter for both of the coefficients that we're learning, except we also notice something interesting. This is not circular. A Gaussian distribution or a normal distribution usually follows a circular pattern, right? So it's a bell which is shaped as a circle, but this is more of an oval, which means that our posterior distribution is providing us unique value compared to just sampling from a normal distribution. And that means that while our average team age is really informative, and we know that the parameter is exactly here, there might be a lot more variability in the vertical axis, which is the amount of certainty we have for the coefficient for the games won last season in terms of the parameter that is the optimal one. And that allows us to glean some uncertainty about how we should use this feature, especially when we have many, and when we want to know how uncertain is our model over the coefficients that it's learned. So I know there's a lot of information that we covered in those last few minutes. So to summarize, the value of Bayesian machine learning is that we are able to understand uncertainty by sampling from the possible forms that our model may take and seeing how that model fits as we give it more and more data. So while this posterior distribution seems to tighten, there still is some variability. So then when we look at the parameters and how uncertain we are in the parameters, we see that that uncertainty is coming from the games won last season, which may follow a wider posterior distribution for that parameter's value. So now going back to the slides, at this point, we're close to the end of the presentation. So I do want to take some time to say thank you to the Delta Analytics team. So I want to thank Alicia for mentoring me, editing my slides, providing feedback, and spending many Saturdays both reviewing, talking with me, and helping me really improve this presentation so it adds the most value to those watching. I want to thank all of the teaching mentors for their Saturdays as well, the hackathons, and giving us the opportunity to really learn the skills to share our knowledge with others and give other people the opportunity to really dive into machine learning. Those teaching hackathons have been a great time for us to both learn and interact with one another, but also come away with some really concrete skills on how we can teach others. And lastly, but certainly not least, I want to thank the other Global Teaching Fellows for all their support, jokes, and the sense of community that they've provided during hackathons and in prepping for these graduation lectures. So I want to also provide some resources for going beyond just this lecture. So there's a couple of links that I've provided here. I'm, of course, open to answering any questions, so please feel free to email me at sharma.kri@northeastern.edu, reach out to me over Twitter, or my GitHub is also linked, so that also has my contact information on there. And with that being said, I want to open it up to questions, so if there are any, please feel free to ask. Thank you. Really appreciate you coming out and spending your time to listen to my talk. I really, appreciate that. So the coding example of a distribution that does not fit a Gaussian distribution is really helpful for understanding variance and uncertainty. Yes, for sure. So definitely agree. And I think, there's two portions that we really got to see there, which was the uncertainty in the output, which is, the line and the samples for the possible fits, and the uncertainty in the parameters themselves. So while we only model over parameter uncertainty, we're able to glean information about both output and the model itself. Thank you very much. I really appreciate that.
Okay, thank you everyone for coming to our Delta Analytics Global Teaching Fellow lectures. This is our first lectures. And if you enjoy this talk, we're going to have even more lectures coming in soon. And with that say, we have concluded today's lecture. And thank you so much, Krish.
Thank you.
For your lecture today.
Yes, of course.